Modern neurocritical care is essentially defensive. When a patient suffers a traumatic brain injury, the immediate priority is stabilization, controlling intracranial pressure and optimizing blood flow to prevent the initial damage from spreading. For decades, researchers have tried to go further, spending billions on clinical trials that target isolated molecular pathways triggered by the impact. Yet nearly all of these interventions have failed to improve patient outcomes. This impasse suggests we are looking at the wrong set of variables. The initial trauma creates a toxic milieu, a microscopic debris field of damaged proteins and cellular waste that remains trapped in the tissue long after the patient is stabilized. Current research suggests this debris is not just a byproduct of the injury, it is an active driver of ongoing pathology. If the brain cannot clear these toxic elements, the surrounding healthy neurons are forced to survive in a poisoned environment. This shifts the focus of recovery. If the damage is sustained by what remains in the tissue, then long-term healing may depend less on preventing the initial strike and more on restoring the brain's internal capacity for cleanup. To understand how to facilitate that cleanup, we have to view the brain as a dynamic fluid environment rather than a static organ. This chart illustrates the glymphatic system, the brain's internal conveyor belt. Cerebrospinal fluid is driven along arteries by natural pulsing, washing through tissue to collect waste. It's then funneled toward the meningeal lymphatics of the dura mater and flushed into the body's peripheral immune system. A third pathway involves the blood-brain barrier. While it normally acts as a strict gatekeeper, a traumatic injury causes it to fail, creating a chaotic overflow where brain-derived proteins leak directly and unregulated into the bloodstream. For the brain to maintain a healthy internal state, all three of these pathways must work in a seamless, coordinated loop to remove the debris generated by daily neural activity. A traumatic impact acts as a physical bottleneck for this entire loop. The resulting swelling collapses the glymphatic channels, inflammation clogs the lymphatic drains, and the barrier failure creates an unregulated mess. The waste is effectively trapped. There is also a physiological constraint. This clearance system is largely inactive while we are awake. During slow-wave deep sleep, the spaces between brain cells expand, allowing fluid to surge through and wash away the day's metabolic waste. This creates a self-sustaining cycle of damage. Traumatic brain injuries almost always disrupt the natural sleep architecture, robbing the brain of the specific physiological window it needs to flush out the debris causing the inflammation. Viewed this way, post-injury insomnia is more than a side effect. It is a structural failure of the waste removal engine that keeps the brain in a state of chronic toxicity. This clearance-based framework helps explain why certain protein biomarkers associated with brain damage stay elevated in a patient's blood for months after the initial impact. Traditionally, doctors interpreted these lingering levels as a sign of continuous, irreversible cell death. This diagram in Section B offers a different perspective. It shows large structural proteins, like GFAP, being extruded into the fluid surrounding the cells. If clearance pathways are blocked, these proteins can't escape. They linger and slowly leak out over months. These persistently high biomarker levels are a dual signal. They confirm the initial injury and document the ongoing failure of the brain's plumbing. Recognizing this has led to the development of neurofluidic therapy, a new approach that aims to optimize the movement of fluids within the brain to accelerate recovery. One experimental method, shown here in Section C, is photobiomodulation. By applying near-infrared light to specific points on the head, researchers are attempting to stimulate cellular energy and manually increase the rate of lymphatic drainage. Because this system is so sensitive to the sleep-wake cycle, these treatments must be used as a form of chronotherapy, aligned precisely with the body's natural rhythms to maximize the brain's internal washing phase. Moving these therapies into the ICU requires a rigorous stepwise roadmap. As this chart shows, the field must progress from mechanistic foundations to feasibility studies before these interventions can be tested in large-scale clinical trials. By making clearance a central target, neurocritical care can evolve from stabilizing vital signs to supporting the specific biological processes that drive actual, long-term recovery.